In the world of AI, the race has always been about one thing: getting bigger, more powerful models. But a few years back, researchers, they slammed right into a wall, a computational wall. Scaling up was just getting so incredibly expensive, so resource-heavy, that it really felt like we were hitting the absolute limits of what was even possible. But then, one paper came along, and it didn't just break through that wall, it found a completely different way around it. And, in the process, it changed the entire game forever.
So this was the the trillion-dollar question facing the entire field. See, everyone knew that more parameters, you can think of them as the little knobs and dials inside a neural network, led to smarter, more capable models. The problem was, with the way things were being done, more parameters meant exponentially more computation. And that costs an absolute fortune. And that's what we call the scaling wall. The standard design at the time, a dense transformer, activates every single one of its parameters for every tiny piece of data it looks at. To put that in perspective, imagine trying to read a book, but for every single word on the page, you had to reread the entire library. Yeah, it's incredibly thorough, sure, but it is horrifically inefficient. The computational budget was just running out. Think of it this way. A dense model is like a single genius doctor who's trying to be a world-class expert in everything. We're talking cardiology, neurology, pediatrics, brain surgery, all at once. They can probably do it, but it takes a ridiculous amount of energy for every single task. This was the brute force approach to AI, and it was becoming crystal clear that a smarter strategy was needed. Fast. So the first real hint of a solution was this idea called mixture of experts, or MOE for short. The thinking was, instead of one overworked generalist, why not build a whole team of specialists? In an MOE model, you have different parts of the network, these so-called experts, that specialize in different kinds of data. Then, a smart routing system looks at the information coming in and sends it to the right specialist. This is called a sparsely activated model. You can have a huge total number of parameters, but you only wake up a small fraction of them at any given time. But, and there's always a but, these early MOE models had some serious issues. The routing systems had to be incredibly complicated, partly just to balance the workload. Making sure some experts didn't get buried in work while others just sat around doing nothing. This created all sorts of data traffic jams, and the models themselves were notoriously unstable and difficult to train. They were so fragile, in fact, that they often had to be trained using higher precision numbers, which just slowed the whole process down even more. The promise was there, for sure, but in reality, it was a mess. And this is where the switch transformer paper had its absolutely brilliant insight. The entire field had basically assumed that to make MOE work, you needed a smarter, more sophisticated router. It needed to send each piece of data to multiple experts to get a good result. But these researchers asked a simple, almost naive question. What if we just didn't do that? What if we did the opposite? And the solution was just stunningly simple. The old MOE approach, the one that was so unstable, it would send each little piece of data to the top 2 or maybe more experts, hoping they'd work it out. The switch transformer's big breakthrough was to just pick one. It routes each token to only the single best expert for the job. That's it. They turned a complex routing problem into a simple on-off switch. It was a move so simple it seemed like it had no business working. But oh, it did.
This one simple switch created this incredible cascade of benefits. First off, the router's job got way easier, which saved a ton of computation. Second, since each token was now only going to one expert, the capacity, or the waiting room, for each expert could be slashed, saving precious, expensive memory. And finally, the whole system just became simpler, which meant less communication overhead between all the parts and, frankly, fewer things that could go wrong.
So here's the crucial question. Did it actually work in practice? Absolutely. Take a look at this chart. It shows training speed. The higher the bar, the faster it is. The standard dense model, T5 base, is pretty fast. The old MOE approach, much slower. But now look at the switch transformer. Okay, it's not quite as fast as the dense model in raw throughput, but it's a massive improvement over the old MOE system, and its overall efficiency is where it really shines.
And that efficiency leads to just staggering speed gains. If you had the same computational budget for both, a switch transformer could reach the same level of performance as its dense counterpart 7 times faster. Let that sink in for a second. What took a full week of training could now be done in a single day. A game changer.
But it gets even more impressive than that. The architecture was so efficient that it was 4 times faster than T5XXL, a truly gargantuan dense model that was orders of magnitude larger. It was like watching a finely tuned sports car blow past a gas-guzzling freight train. This was the proof. Smart architecture could finally beat brute force.
Now that top 1 router was the star of the show, no doubt about it. But the paper also introduced a few other really clever tricks to tame these massive models. They use higher precision math just for the sensitive router calculations, kind of like using a surgeon's scalpel for one delicate part of an operation. They also tweaked the model's starting parameters and used a targeted type of regularization called expert dropout to keep it from getting lazy and overfitting. These were the nitty-gritty engineering details that made the whole system robust and stable.
And with that beautifully simple switch router, combined with all this clever engineering, the team was finally able to build this, a model with 1.6 trillion parameters. At the time, that number was just astronomical. It was something people thought was years away, if not impossible. The simple idea of a switch had officially unlocked the trillion parameter scale.
And that's the real legacy of this work. It was never just about building one giant model. It was a paradigm shift. This paper showed the world that the path forward wasn't just about throwing more and more computation at the problem. No, the new frontier was efficient, sparse models that could scale their knowledge, their parameters, without scaling their cost at the same insane rate. This blueprint is now right at the heart of many of today's most powerful AI systems.
So here's the thought I want to leave you with. This entire breakthrough came from challenging an old assumption and replacing a really complex system with a radically simple one. It just makes you wonder, right? What other huge, complex problems in AI are we just overthinking? What other incredible progress is just sitting there waiting to be unlocked? Not by a bigger supercomputer, but by one simple, elegant switch.
This is for entertainment purposes only.